Happy Friday. Another week. We left off. We had just started looking at circulation of, what was it, 1 over x squared plus y squared plus 1, where the curve, let's call it the unit square. Each side has length 1. We said, oh, well, since it's circulation, it's a closed path, so we have to start in at the same point. So we're going to have 4 sides that we have to integrate over, 4 paths. Since it is circulation, does it matter where we start? No, right? We can start anywhere as long as we end at the same point. Why not just start at the origin? Now we do have a direction. Right? So if we're going to start the origin, to travel along the x-axis to 1, 0. Then we're going to have to travel straight up to 1, 1. Then to the left to 0, 1, and then back down to the origin. We're going to call this C1. That's C2, that's C3, and that's C4. We need to parameterize each curve. Start with C1. Bless you. Correct, so what's your parameterization? Right, let's just be T0. X is changing. Y stays constant, specifically at 0. And then T goes 0 to 1. Right, parameterize C2. Well, X is constant. Right, it's always 1. Y changes. Specifically from 0 to 1. C3. Y is constant. Right, so I'm going to keep Y at 1. What about X?
Do 1 minus t.
For what t?
0.
Is that the only choice? And that's what I'm going to use. Couldn't you also do just t? As t goes from 1 to 0? Right, so instead of 0 to 1, it'd be 1 to 0. Which, by the way, if you took the integral, would be minus the integral from 0 to 1 instead of plus. All right, which brings up a good point, right? Parameterizations are not unique. Nothing says t has to go 0 to 1. I could do for C1, right? T over 2. T goes 0 to 2. If I wanted to. That'd be a parameterization. Could have done t squared from 0 to 1. That'd be a parameterization. Right? So they're not unique. So you don't have to think about there's only one. Right? You might have a different parameterization from, someone else for the same curve, and they both could be correct. C4, x is clearly going to stay at 0. And then same situation. Y could be 1 minus t from 0 to 1, could be t from 1 to 0. This is the parameterization I'm going to stick with. So here are the 4 parameterizations. Right, so remember, if you're taking path integral, where your path is the union of non-overlapping paths, it's just the sum of each individual path integral. Right? It's the equivalent of if your domain is the union of non-overlapping domains, right? You can split your integral up and sum it up over each domain. I think we did a problem like that when we were doing double integrals. You saw it with single integrals. So the first curve, all going to go 0 to 1, which is nice. But our parameterization was t0, right? So we're going to evaluate the integrand over that parameterization. 1 over t squared plus 1. dr is the magnitude of the derivative dt. Remember, C2 was 1t. C3 was 1 minus t1. And then C4 was 0, 1 minus t. So there's the setup. Now it's just a matter of evaluation. Notice each of these magnitudes. 1, right? That's nice. Since each integral is over the exact same angle, you could technically write this as a single integral. But considering none of the integrands are common, that really doesn't serve a purpose. Right, there'd be no simplification. So we'll just evaluate each one individually. Because I am too lazy to actually pull out my physical chart. I'm just going to open it up here. Antiderivative of 1 over t squared plus 1. Not tangent. Your mind's in the right place. You used the wrong function. The inverse tangent. Now that's going to get evaluated from 0 to 1. Right, so I'm just going to go ahead and write that. Antiderivative of dt over t squared plus 2. This is why I opened up my table of integrals. It's number 16 on the table of integrals that I handed out. One half inverse tangent of t over 2. Again, that's going to be from 0 to 1. I'm sorry, it's not 1 over 2. It's 1 over root 2. For here, we're going to have to do a u sub. Derivative is -1. So instead of plus, it's going to become minus. Then it'll be 1 over root 2. Inverse tangent of 1 minus t over root 2. But again, there's going to be from 0 to 1. And then that last one would just be inverse tangent of, well, negative inverse tangent of 1 minus t. Again, from 0 to 1. Inverse tangent of 1 is what? Pi over 4. What's the inverse tangent of 0? Zero. Okay, so that's gone. What is the inverse tangent of 1 over root 2? Just the inverse tangent 1 over root 2. That does not have a nice answer, right? Because the question is, tangent of what angle gives you 1 over root 2? Some not really nice angle. Again, inverse tangent of 0, 0, so that's gone. Then we get another plus 1 over root 2. Inverse tangent of 1 over root 2. 0, and then minus negative pi over 4. There's the circulation. Pi over 2 plus root 2 inverse tangent 1 over root 2. Or if you write that as 2 over root 2, that's also fine. Now, bear in mind that, while tedious, right, was a relatively simple closed path. I mean, those parameterizations are not terrible at all, right? Those are actually very nice parameterizations to work with. You can get some really hideous looking closed paths. You said scroll down slightly?
Did say that.
There, I scrolled down on slightly. How far down do you want to go? And all we did was write the circulation as the sum of the four paths. Right?
Go back up a little.
That's probably what you're going to want, the parameterizations. And again, that looks bad. But you could theoretically have a closed path that is 50 individual paths. Now that is just awful mean. Unless I make it circulation of a certain type of vector field, in which case it is then really easy. We cover that next week. Oops, that's not number 2. What am I doing? This is 4. Find total work done in moving a particle in the force field given by ZZX along the helix cosine of t, sine of t, t, from t equals 0 to t equals pi over 2. All right, so if you don't remember, helix looks like a spring. Right? In this case, it's spiraling up the z-axis. Right? You could also have a helix spiraling along the y-axis or along the x-axis. Right? You just adjust the parameterization accordingly. Which means we need to discuss work. So we've now looked at a total of 4 scenarios for work. Right, first one is the easiest, where it's a constant force applied over a straight line distance. In which case work is just force times distance covered. Second scenario is it's a variable force moving in one dimension. Then it's just the integral of the force with respect to x. Then we did what was it? A force vector moving along a position vector, right? And it was F dot R, but force was constant. Right, so it was essentially the equivalent of a constant force moving in straight line, except now it's constant force moving along some path. That was F dot R. Now we look at moving through a force field, where essentially it's now a force vector that is variable. Well, it's going to be an integral. Specifically, integrating over the path of f dot dr. Right? It's the equivalent of moving from constant force in one dimension to variable force in one dimension, where we integrated. Path C. I want to use C. All right, so it's the path integral of f, obviously dot dr, right? And you just integrate over the path. Well, that now leaves the question, how do you evaluate the path integral of a force field, of a vector field? Right, because we just did scalar functions. Do the RT. Very similar, except now instead of dr being the magnitude, dr is the derivative of the parameterization, dt. And now we take a dot product. And again, this just means we're evaluating the vector field over the parameterization R. Well, they already gave us the parameterization here. And it's cosine t, sine t, t, 0 to pi over 2. So our work, the path integral of our vector field, zzx dot dr, which will be the integral from 0 to pi over 2, evaluate f over the parameterization. So x is replaced with cosine of t, y is replaced with sine of t, z is replaced with t, right? Because that was the parameterization. Dotted with the derivative of the parameterization. dt. T times cosine of t minus t times sine of t plus cosine of t. That is the dot product. This is where the fun is. Let's assume that I'm in a particularly bad mood and I say you're not allowed to use a calculator or a chart. You have to do this by hand. How'd you go about evaluating that first piece? A single application of integration by parts in this case. How would you go about evaluating that one? Yeah. Again, just a single application by parts would work here. If I was particularly evil, I would make each one like e to the t cosine t and then e to the t sine t. And then maybe the last one e to the t cosine sine. Just to throw a monkey wrench in and then go, oh, yep, have fun, do it by hand. That last piece is simple. But I'm not in a bad mood right now. In fact, it's a Friday. And we all want to go home. Formulas number 37 and 38 will give you t cosine t and t sine t. Be careful here. I did mine out of order. Bless you. Okay. So that's for t cosine t. That would be negative t sine of t. And then obviously cosine t is just sine t. Cosine of pi over 2. Uh-oh. Cosine pi over 2. 0. Sine of pi over 2. So pi over 2, that first term is pi over 2. Cosine of 0. Sine of 0. 0, right? Actually, in this case, doesn't matter because 0 times anything will be 0 anyway. So there's the first term. That'll be 0. Get a -1. That'll be 0 and 0, so just a -1 there. And then sine of pi over 2 is 1. Sine of 0 is 0. Work done is pi over 2 minus 1. What is the prereq for intro mechanics? Is it just Calc 1? It should be Calc 3. Because this type of work is an intro mechanics problem. Bless you. And again, for intro E&M should also be Calc 3. But I think it's only up to Calc 2. Suppose a force field is given by that not as nice looking force. You want to find the work done in moving a particle once around the circle in the XY plane with its center at the origin and a radius of 3. That is what we're calculating. Right, notice this is a circulation because we're traversing the circle one time, right? It's one full revolution. So how are we going to parameterize C?
Cosine T sine T.
Not quite. It's incomplete.
That's 0.
Yes. Two reasons. One, they told us it's in the XY plane, which means Z is 0. 2, notice the force has Z in it. So our parameterization has to be 3-dimensional. And again, technically it's incomplete as it stands. Remember, you always need a domain. So what would your domain be? Why do you say 0 to 2 pi?
It's like that.
Right, but why not pi to 3 pi? Or pi over 2 to 5 pi over 2? Let's get really crazy. Pi over 4 to 9 pi over 4. Like do like what? Pi over 12 to 25 pi over 12? I mean, we could get some really crazy things. So why 0 to 2 pi? Pi because it's the most obvious,
Gotcha.
right? It's what you think of. Doesn't matter, does it? Again, it's circulation. Does your starting point actually matter? No, as long as you end at the same point. So as long as you do one full revolution, which is 2 pi, it does not matter where you start. So you could start at pi over 2 and do one full revolution from there. Hell, you could start at 3 pi over 2 and do one full revolution. And notice they didn't give us an orientation. So we're assuming counterclockwise. Bless you. Right, so work will be the integral from 0 to 2 pi.
You said we're assuming we're going counterclockwise?
Yes,
Why?
because that's always what you assume unless specified otherwise.
Oh, okay.
Always assume a positive orientation. We need to rewrite the integrand. Everywhere there's an x, we get 3 cosine t. Everywhere there's a y, we get 3 sine t. And everywhere there's a z, we just put in 0. So there's f of r. Dotted with r prime. dt. Do the dot product. Squared. Sine, and oh, that 0 is really nice. We do not need any kind of aid with this problem. It looks hideous, but this is a very nice problem. First off, these are going to simplify down to -9 cosine sine, which would be a u sub, right? You could let u be either sine or cosine, doesn't matter. But no matter which one you choose, we're integrating over one full period of it. So both those terms are going to integrate out to 0. Then you're just left with 9 sine squared plus 9 cosine squared, which is 9. You get 18 pi. It didn't look too hopeful when we first wrote it out. That looked like it was going to be really hideous, but it actually worked out to be very nice. Questions on line integrals? So remember, you can take the line integral of both a scalar function and a vector field.
Can you show me, just like review how you did the parameterization of the other problems as well? If you would, or,
Which problem?
the, whatever X squared was Westford. As well.
The square?
Yes.
So you understand the breakdown, right? C1, C2, C3, C4. Just picking paths. Because it's circulation, starting point doesn't matter, so we just assumed that we're starting at the origin. Because it really doesn't matter as long as we go back to the same point. So I just arbitrarily chose C1, C2, C3, C4. So look at C1. You want a parameterization for it. Well, X goes from 0 to 1, right? Y stays constant. Specifically at 0. So why not just parameterize it as T0 and let T go 0 to 1? Again, that's not the only choice. Right? Theoretically, each curve has an infinite number of parameterizations. This is just the simplest. C2 used a similar kind of argument. X stays constant at 1, right? Y is going to go from 0 to 1, so 1t as t goes from 0 to 1. Then we get to C3. Y staying constant at 1, right? So just set your y component to be 1. But now your x goes from 1 to 0. Right, so you have a couple choices. You could do t, but then you'd have to remember that you're going to integrate from 1 to 0, not 0 to 1. Right, because of the direction. Or if you want to stick with 0 to 1, write it as 1 minus t. And then t would go from 0 to 1. And then a similar argument for C4. Again, they're not the only parameterizations. They're just the one that I used. Anything else? Alrighty. I'm about to ruin your breakfast. Well, maybe not. Maybe this would improve the breakfast. Next week, we're going to look at the fundamental theorem of line integrals and do surface integrals. Oh boy. Surface integrals suck. Ever heard of a little thing called flux in physics? Yeah, those are surface integrals.
So maybe we start to the semester, you could really try it on these programs.
By the way, if you already know the fundamental theorem of line integrals, you're not allowed to use it on this. And then when this is finished, if you want to stick around to do any makeup quizzes you have in, we can do that.